Hello, and welcome to our first discussion of series solutions for ordinary differential equations. Here is our motivation. How do we solve a linear ODE with variable coefficients? So something like f double prime plus a1 of x times f prime plus a0 of x times f equals g of x, where in particular a1 and a0, those coefficients, are not necessarily constant. Well, one thing we know is that there's always a solution, at least in the case when a1, a0, and g are continuous. We proved some theorems about this earlier in the course. So you know a solution exists. But the question is, what is its formula? What can you calculate or say about it more explicitly than just existence? We know if we have a fundamental solution set for the homogeneous problem, f double prime plus a1 of x times f prime plus a0 of x times f equals 0, then we can use variation of parameters and get an integral representation for the solution depending on the fundamental solution set and also on g. So how do we find a fundamental solution set? Maybe the better question is to ask that rather than trying to solve the whole non-homogeneous equation. In the case that a1 and a0 are constants, we certainly know how to find a fundamental solution set. You just do the characteristic equation method. But what if they're not constant? What if they can change as x changes? Well, here is an idea. If a1 and a0 are real analytic on an interval centered at some point x0, then we might guess that a solution f will also be real analytic on some interval centered at a point x0 as well. In other words, the nicer the coefficients are, the nicer a1 and a0 are, the nicer f ultimately should be. And then you would have an expression like f of x is the sum from k equals 0 to infinity of ak times x minus x0 to the power k, and that expression for f would be completely determined by its coefficients ak. And one nice thing is that instead of trying to find uncountably many values of f of x for all those different x's, we would just have to find a countable sequence of numbers ak, this sort of list or set of coordinates for f, and that would completely determine f. So what if we guess that f is a power series and plug that back into the differential equation? What might happen? So we're going to look at an extremely easy example in this first video, f prime equals f. And we're going to guess that f of x has the power series expansion sum k equals 0 to infinity of ak times x to the k. So for simplicity, we're centering this power series at x equals 0. And of course, we want to get the expected result. F of x is a constant times e to the x, which is a constant times the sum k equals 0 to infinity of x to the k divided by k factorial. The purpose of this example is not to derive anything new, but just to see how some manipulations with power series inside a differential equation would work. So let's do that. Let's guess that f has this power series form. If so, we need to know what f prime is. So then f prime of x, just by our rules for differentiating power series, will be the sum from k equals 1 to infinity of k times ak times x to the power k minus 1. And then we're going to substitute this into our differential equation. So we want the sum from k equals 1 to infinity of k times ak times x to the k minus 1 equal to the sum from k equals 0 to infinity of ak times x to the k. So on the left I have f prime, and on the right I have f. And just subtracting, that tells me the sum from k equals 1 to infinity of k times ak times x to the k minus 1 minus the sum from k equals 0 to infinity of ak times x to the k has to be 0. Okay? Can I clean this up at all? The answer is yes. We are going to do a technique called reindexing. So say that you have a series sum k equals 0 to infinity of bk. Here the bk's are complex numbers. This could be a power series with x fixed. Maybe it's just a plain old series, doesn't really matter. And say you have an integer m. Then the sum from k equals m to infinity of bk is equal to the sum from k equals 0 to infinity of bk plus m. So if you switch around the lower index of summation and the index inside the series, you can rewrite that sum in two different ways. And specifically, we'll look at our sum from k equals 1 to infinity of k times ak times x to the k minus 1. That starts at the starting index k equals 1, and we're going to bring that down to starting at k equals 0 by rewriting this now as the sum from k equals 0 to infinity of k plus 1 times ak plus 1 times x to the k plus 1 minus 1. So what did I do? I brought down the starting index from k equals 1 to k equals 0 in the sum, in the sigma notation, and inside the sum, I bumped up k by 1 every time k appeared. So now the power series for f prime really reads sum k equals 0 to infinity of k plus 1 times ak plus 1 times x to the k. And what's important is that when I plug this back into my ODE, all the series, all two of them, are going to have the same powers of k at each step, x to the k, not x to the k minus 1 and x to the k. So the ODE f prime minus f equals 0 is now 0 equals the sum from k equals 0 to infinity of k plus 1 times ak plus 1 times x to the k minus the sum from k equals 0 to infinity of ak times x to the k. And let's group that together in one series. This is the sum from k equals 0 to infinity of k plus 1 times ak plus 1 minus ak times x to the k. Now the identity principle for power series is going to tell us what this becomes. I have a power series that's equal to 0 for all x. That means the coefficients are always 0. Namely, k plus 1 times ak plus 1 minus ak equals 0 for all k. And so we'll solve for ak plus 1. That tells us ak plus 1 is equal to ak over k plus 1 for k greater than or equal to 0. In other words, it tells us what each coefficient, a1, a2, a3, and so on, is in terms of its immediate predecessor. ak plus 1 depends on ak. We don't know what a0 is. This formula won't tell us what a0 is, but we expect a free parameter in a first order ODE anyway. We expect sort of one constant of integration. So we expect, or at least can accept, that we won't be able to determine every single coefficient. There'll be one coefficient that's left over free. Now this is really a recursion relation for ak plus 1. We've written ak plus 1 in the form ak plus 1 equals phi of ak and k, where here phi is a function of two variables, a complex variable z and an integer variable k. Phi of z is z divided by k plus 1. So that's a nice formula for ak plus 1. It's a simple formula. You could plug it into a computer, into MATLAB or whatever, and write a for loop and calculate out a bunch of these values ak. But we are tempted to ask, and we should ask, can we do a little better? Can we get a formula for ak plus 1 purely in terms of k? Can I write something like ak is equal to psi of k for a function psi that goes from the natural numbers to the complex plane? Because if I could do that, then I wouldn't have to worry about computing ak before I computed k plus 1. I wouldn't have to compute these coefficients all in order. I could just compute ak for my favorite number k. And so to do this, it's helpful to calculate ak plus 1 for some small values of k and see if there is a pattern or an obvious formula that emerges. So a1 is equal to a0 plus 1, which by the formula is a0 over 0 plus 1, which is a0. Not exactly exciting there. a2 is a1 plus 1, which is going to be a1 over 1 plus 1, which is a1 over 2. And now I use my formula for a1, that's a0 over 2. Keep going, a3 is a2 plus 1, which will be a2 over 2 plus 1, which will be a2 over 3, which is a0 over 3 times 2, using my formula for a2. a4 is a3 plus 1, which will be a3 over 3 plus 1, which will be a3 over 4, which will be a0 divided by 4 times 3 times 2. a5 is a4 plus 1, which is a4 over 4 plus 1, which is a4 over 5, which is a0 over 5 times 4 times 3 times 2. a6 is a5 plus 1, which is a5 over 5 plus 1, which is a5 over 6, which is a0 over 6 times 5 times 4 times 3 times 2. And the general pattern that seems to emerge out of this is that ak plus 1 is equal to a0 over k plus 1 factorial for each k greater than or equal to 0. And we could rewrite this, of course, as ak equals a0 over k factorial for k greater than or equal to 1. Now, to prove this rigorously would require induction, and we will not require induction in this course. So we'll just, when doing these kinds of problems, look at a listing of values of ak for relatively small k. You can usually do this for k less than or equal to 10, and a pattern will come out, and we'll take that to be the formula for the coefficients. And so we conclude f of x, we guessed was the sum from k equals 0 to infinity of ak times x to the k. And now we know what ak is. This is the sum from k equals 0 to infinity of a0 over k factorial times x to the k, which will be the sum from k equals 0 to infinity of x to the k over k factorial times a0, and that's a0 times e to the x. So f of x is an arbitrary constant times e to the x, which is, of course, the general solution of this ODE. In our subsequent video, we will examine this a little more closely and understand under which conditions on the differential equation we're justified in making the power series onsets, and how we know that the power series is going to converge and where when we deal with a much less familiar differential equation than just exponential growth.